Oh, that's it. Okay. Peter. We're going to sing both official versions of O Canada together. So would you please stand and sing O Canada, if you are able to. Oh yeah, now they got you standing, you know, let's try to sing it. No, not the nice word. Starting on I didn't want to go D or B flat, it's too low. Guys would love it. Except for tenors.
O Canada, town and O Zion, true faith is now, if our sons through land, with growing hearts they see, rise strong, marched and free, from the far and wide, O Canada, we stand on guard for thee. God gave our land, glorious and free. O Canada, we stand on guard for thee. O stand on guard for thee.
Drop the puck.
Give yourselves a hand. And a little trivia for you. If you're at a hockey game and the guy goes, "Oh Canada, we stand on guard for thee." Calixa Lavallée never wrote it that way, and I played it on a trombone with a band. It's always going down. You get the Hollywood types that like to go up. So thank you very much. Give yourselves a pat in the back. You're a good chorus. I think I might hire you.
All right, good afternoon, everybody. Welcome to the next stage of our maple-flavored General Assembly, Maple GA. All right, just a quick question first. Are there any members of the public here who were not part of the General Assembly who have come in for the presentation? At the back, that's great. Okay, nice to see you here. We have one of our astronomy educators on board today, Paul Cloninger. Paul, with his hand up there. If you've never put a planisphere together before to work out how to work the stars, Paul will be happy to work with you as well. We are having a little reception right afterward. We're a rather small group. You're welcome to join us for that as well, please. All right, and I'll invite our Ottawa Centre President, Tim Cole, up just to read the introduction as we get on with the RUTH NORTHCOTT lecture.
Well, folks, the RASC runs a biennial series of lectures in honor of RUTH NORTHCOTT, a lady that most of you, well, the RASC has undoubtedly heard, but many of the general public haven't, and that is a vast disservice. She spent a considerable amount of her career looking at such arcane details as motions of double stars, which may seem rather trivial to members of the public, but this stuff is how we know a great deal of the universe around us. She has also served many, many years with the Royal Astronomical Society, acting as editor of the Journal of the Royal Astronomical Society and the Annual Observer's Handbook. So this series of lectures is intended to cover a wide variety of topics that we hope will be of interest to both the RASC membership and members of the public who choose to come and join us. So, welcome, and Brian?
Thank you. Thank you, Tim. As we selected our speakers for the General Assembly, we did it with some care, I have to admit, because we, as you know, for our keynote speaker, we wanted somebody talking about the RASCs. We had Ken Hewitt-White. We're bringing in different speakers who can, I think, give us different perspectives on amateur and professional astronomy. And for our RUTH NORTHCOTT lecture this afternoon, we relied on my daughter for a good suggestion, a recommendation on who to invite. Our daughter's done she's a PhD astrophysicist. She works up in, does occasional work up in the high Arctic. And this is where she ran into our lecturer, Dr. Eric Steinbring here. And he was setting up small telescopes and looking at the mountains on Ellesmere Island, looking at potential sites for siting some small telescopes. So he's done a number of interesting things that way. He comes to us from as a senior research officer from the National Research Council, the Hertzberg Institute in Victoria. And he's involved in studying quasars and galaxies, and it's all high resolution imaging that he's involved with. And he's also involved with the aspect of adaptive optics, because remember, we're working from ground-based observatories. We've got a very thick atmosphere to go through, so he's been looking at different locations around the world in terms of how can we, what's the best place to site telescopes. So he's got a number of different areas of interest that are of interest to us. And it was really great picking up Eric at the airport last night. We zipped right out to the Defen bunker for a quick look-see at things. And please join me in welcoming Dr. Eric Steinbring. Eric.
Hi there. What an honor it is to be speaking to you today about astronomy from coast to coast to coast. So as Brian mentions, I do astronomy from different parts of the world. I do adaptive optics, and so you need to go to the best places to do that. You need really good seeing. And so I go to Chile and Hawaii. I know it's a tough job to do astronomy. But today I'm going to talk about astronomy from Canada, and a great site in Canada, which we don't normally think of great sites, but we, amongst this audience, we have people from all over Canada, from coast to coast, but not quite from coast to coast to coast. I bet you there's some here from pretty far north, like Edmonton, for example. Whitehorse. Iqaluit, that's pretty far north, but not from Eureka, right? Okay. Eureka and Alert are the farthest north you can go in Canada, and they're in Nunavut. So we're going to go on a little trip to Nunavut. And Nunavut goes very far north. Alert is 82 and something degrees north. You're less than 500 nautical miles from the North Pole. And Nunavut is the newest territory in Canada. And it is difficult to get to, but there are towns. There are places to go to. You can go to Iqaluit. You can go to a place called Resolute Bay. And Resolute Bay has a research base from which you can get to all over the high Arctic. And it's operated by Natural Resources Canada through the Polar Continental Shelf Program. So some of this trip will be through Resolute Bay, some of it from Yellowknife. But all of this, what I'm going to be talking about, is in Nunavut. And Nunavut's flag, which is in the lower right-hand corner here, is the red structure in the middle is the iconic Inukshuk. So this is a stone waymarker, how you find your way around in the north. And the star is Polaris. We're going to talk about Polaris too. The thing about Nunavut, that's supposed to go up and stay as a geographical map. So there are mountains. So the northern part of Ellesmere Island, as far north as you can go in this plot, there are mountains that run all along here, and they're quite high. The highest is 2,600 meters. The mountain that I go to in Chile for the Gemini North telescope is 2,700 meters. So these are very high mountains. It's a very cold, dark location. Well, this is going to be great for astronomy. So that's what this talk is going to there and seeing how good that is. Well, as I mentioned, we're going to talk about astronomy from coast to coast to coast. So I'm from Victoria, the Dominion Astrophysical Observatory, and it's about the same distance from Hawaii as CFB Halifax is, and also these places up here on the northern end of Ellesmere Island. They're about the same distance, a little closer actually, but they're not as easy to get to. Here's some more pictures to show where we're going. As you can see, this is the northern Ellesmere Island. This is the place called Eureka. Eureka is a real base. You can fly there in the winter time. You can't do that in Antarctica. Fly there in the middle of the to South Pole, for example. Fly there in the middle of the winter time. There's a 5,000-foot runway. There's a research base here, this blue building, which supports a crew a rotating crew of 8 people. And from there, you can drive in a regular diesel pickup truck up a road to this place, which is PEARL. It's the Polar Environment Atmospheric Research Laboratory, and it's really an observatory. It was designed to do atmospheric research studies. There are LIDARs there, and other optical and atmospheric science instruments, and also a flat roof. And so, as many folks here are familiar with, if you can get up on a nice flat spot and put up your telescope, you can do some astronomy. And so this is a great place to do astronomy. It's dark for many months at a time in the wintertime. It's very cold and very calm. This is a great spot. This is shown in the summer, but we'll get there in the wintertime too. To talk to alert, remember alert's at 82 something degrees north. You cannot see a geosynchronous satellite from 82 degrees north, but you can from 80. And so that's what this device here, this is a microwave repeater. And there's a string of these that run down the backbone of those mountains on Ellesmere Island to get to Eureka, where they can see a geosynchronous satellite. So this, I'm not going to talk about these stations in particular, but that kind of infrastructure, like the infrastructure of this building, are important. There's not a lot of places you can go to do astronomy. And in fact, if you want to go anywhere else, essentially, than this iconic red building here, you're going to have to go there on a helicopter. Can't do that in the wintertime, got to do it in the summertime. And so you need to learn how to figure out the logistics of how to do that. But there's lots of research that's going on in the high Arctic and on Ellesmere Island that allows you to do that. And so about 10 years ago, we started a program to go to these particular mountains. These are the farthest northern mountains you can get to in a helicopter in the summer in the world. Only farther north is a national park. Those mountains aren't actually closer to the coast. So this is as close as you can get to the coast. And the reason you want that is because the wind that's blowing on these mountains, these coastal mountains, is coming over hundreds of kilometers of ice. There's nothing disturbing it. So the wind goes over these mountain tops and it's undisturbed. It should have very good seeing. There's no way to mix up the air. And so that's why you want to go to these coastal mountains right on the coast. And we'll have to get there in a helicopter. The alternative to that is to go to the middle of the glacial plateau of Antarctica. That's the only other place on the southern pole where you can get to high elevation and be within the middle of a giant ice sheet. So that's the alternative. And the latitudes is roughly equivalent, right? So that's why this is how this fits in with the world picture. So this is equivalent to going to Antarctica. And so there, for decades, there's been astronomy done from Antarctica, from the middle of the glacial plateau. This is a picture of a base called Dome C. It's at 76 degrees south. 76 degrees south is roughly, 76 degrees north is where Resolute Bay is, which is basically where we start from. And then this is Eureka at 80 degrees north, and some stuff that I've photoshopped in that would be interesting. To be fair, this guy is also photoshopped in. But the reason why it's there and why this tall tower is there is because the glacial plateau is perfectly flat. So that causes a problem. There's a strong inversion. So it's actually colder at the surface than it is higher up. And the problem with that is you need to get above the inversion in order to be in the clear air. The clear, smooth flowing air, which gives you good seeing. So actually, the seeing down here close to the ice surface is bad. It's 2 arc seconds or so. I know that sounds pretty good to most of us here, but that's not to do adaptive optics. You need much better than that. You need better than sub-arc second seeing in order to do adaptive optics, really. And so you can get that just on the roof of this building because it is on a mountain. It's not a flat surface, and so you can get above the strong surface effects and get at the good seeing. It's also similarly dark and similarly cold and similarly dry. So all the other aspects are there. Okay, but if you're not going to go to that roof of that building, you're going to have to go to a mountaintop in the summer, and you're going to have to build a robot. And the robot that you're going to build, kind of like those microwave repeaters, is something that runs on batteries and is independent. Once you lay the thing down on the ground, you step away from it. So that's what these are. These are standard weather station devices that have been put in many places in Canada and the high Arctic. And then you add to it a communications device, because normally those you just go to in the summer and retrieve your data file. We actually want to talk to the thing in the wintertime. And you're going to take pictures with it. This doesn't have a telescope yet. It has a camera in order to figure out how good the quality of this mountaintop sites are. And then we practice. So we put together our meteorological station with its cameras. Here we are testing on a ski slope. This is Mount Washington on Vancouver Island. And you'll notice that guy is a wind turbine. Well, you can't really use solar cells, can you? You can't use a solar panel in the wintertime. It's dark for 5 months. So this thing is powered by wind. And the winds are periodic. You have strong winds every week or two, and then it's perfectly calm. So actually you have to store up that energy in a battery and then use it in the periods in between. And you have to figure out the process of installing it. And then you take it there in the summer. And this is on the top of one of those high mountains. And the logistics are doing that, and of course up in the upper right-hand corner is a picture from the test period, and then here it is, and it should show a picture from when it was installed at the site. But installing at the site means that, like I said, it's a robot. You don't get to touch it after you've installed it. It just runs on its batteries. And so you want to predict how well it will sample the sky conditions when you've left. And so because the winds will pick up and charge the batteries and then they'll die away, you're actually biased to measuring the sky conditions when it's windy. So you have to understand that. So that's a computer model. And that's what this center panel is showing as a prediction based on we know the weather conditions at lower elevation and from other places. We can predict how well this thing will perform. And then we take pictures. Here's a picture under cloudy skies, less than perfectly cloudy, pretty clear. Ooh, that looks good. And so we can count the number of frames that are clear and cloudy, and we figure out the statistics from the site. So we can confirm that these high mountain sites are really as good as we expect. And you learn some tricks along the way. Well, here's another trick. Is you bury those batteries. So you want to bury them in the snow. Snow is a great insulator. And so everything that's electronic is buried in a sealed box. Some other tricks. I could talk for hours about how you build these robots. You have to make sure that everything is electrically connected because it's very dry. And when you have a very dry situation with a spinning prop, you might have electrostatic buildup. And electrostatic buildup is bad for electronics. And for one of our stations, it was very bad. So let's go there. Let's see what it's like to fly to the top of the world in the middle of summer. This is a short video. It lasts about 3 minutes. That is how to go to the tip of Ellesmere Island from Resolute Bay, which is 76 degrees. And so we have our maps. This is one case where I will be telling the pilot on the bush plane that we'll show you in a moment, telling the pilot where to go. You don't normally get to do that, and it's a responsibility you take very seriously because if you don't find the landing spot, you're turning around and going back. This is the camera that we're going to install. The name of that camera is OTTAWA. You'll see a little later. It looks a little bit more like a snowy owl when it's installed. There's our fuel, which we're going to land at our gravel runway by the campsite. We're going to go camp in the summer. It's going to get loaded on the plane. That's a forklift. These are my notes. I take video when I'm doing site testing work, just so I have some video record. It's easier to give a talk about it later, too. This is all our gear. And just like you'd imagine, it's a typical camp. We got cook stoves and tents and check, and shotgun check. Yep, there are bears. So we have to be qualified to deal with that. This is our campsite. And there's our Twin Otter that's just dropped us off. We are, 150 nautical miles from the next human being. And off they go. There's 4 of us in this crew. Bye. See you again in a week. and then it's very quiet. This is a pretty isolated place. There's no hum of the rest of the world here, and we're on our own. And we put up our camp. First thing you put up is the radio antenna, because we're going to talk to Resolute Bay, the base at Resolute Bay, twice a day. If we miss our radio communication with Resolute Bay for more than twice, they're going to send that plane back and get us. Probably won't get to go again, too. Here's our helicopter. It arrives the next day, right on schedule, and flies us to those mountain peaks. There's our pilot doing the checks. I did a lot of flying around in helicopters for this work. A lot of looking between my feet through the glass at mountaintops. This is a 1,900 meter high peak, which I think we nicknamed the Castle. It is quite a complicated, there's no names for these things. There's numbers on a map. So we searched these mountain peaks for safe places to land the helicopter. You can land on snow, you can land on a glacier under certain situations and depending on the wind conditions, and you have to find a place where you can put down the station. This is the highest of 3 locations that we installed those weather stations at. Helicopter coming to pick us up. You can see our tracks in the snow. We've installed the station. This is something that 2 people can do in 2 hours. This is all practice. You press the go button. There's literally a go button, and you walk away. There's Ukpik. Looks like a little snowy owl. Fairly well, little Ukpik. And so Ukpik was more sophisticated in a 2nd generation, and it's really an apt name. So here's that all sky viewing camera, which takes pictures of the whole sky to measure the sky clarity. There's also a seeing monitor. So we need to know how good the seeing is at this site. We don't need a very accurate measurement, but we need to get it above. We need to test it at a certain bar to know if it's good enough. If it's not good enough, we might have to build a taller tower. So that's the question we need to answer. And this little camera stares at Polaris. And if Polaris wiggles too much, that's bad. If it wiggles only a little bit, that's good, because you can also take into account the fact that the station's going to wiggle a little bit too, and you can take that out. So you can figure out how much the stars wiggle about, how much the stars are twinkling, and that tells you how good the seeing is, how good the image quality will be. And because Ukpik's going to run continuously to watch Polaris, you can't just have this wind turbine, which runs, remember that just runs the basic station, the Inukshuk station, as it was called. You also have a fuel cell. NRC has a fuel cell institute, and they figured out with us how to install a fuel cell that'll work at minus 30, minus 40 degrees Celsius and continuously run this station. It also has, when it's in the dark, this top opens up. There's a big ram in here. It's a big worm gear that pushes that lid off. And then when you don't need to observe, like for example when it's sunny, for the other 5 months of the year, you don't really need to look up then. It needs to close. So Ukpik has to go into its burrow and stay safe, because there will be some precipitation in the summertime, and that's not what we want on the cameras. So it closes up. So this is all practice too, so how to install this. And the other item which is kind of interesting is, remember, I'm going to press the go button, and I'm going to walk away. So I'm not going to get to polar align my Polaris telescope in the wintertime, which is when it's easier to do. I have to align it with a mountaintop. So this little device up here is this little jig is what I'm going to use. This is that DAO, and this is looking at Mount Washington from the lunchroom patio at DAO. And this jig allows me to line up. I know my position very accurately from GPS. I know the position of the peak of Mount Washington very accurately from somebody else's GPS measurement. And then I can align that guider to the position on the mountaintop, and then I know my absolute position. I also know my absolute elevation very accurately. You can measure the elevation that thing ticks, sighting telescope allows me to align. And so I have my telescope fixed on Polaris, I trust. But I can test that the next night when I'm at DAO. And so that's what this is doing. I'm correcting for the elevation of Polaris in this case. Remember, this thing's going to be almost flat when we're actually at the site, but I can account for that. And then you go and install it, and you can see it's pretty much straight up. Polaris is always overhead from 80 degrees north, almost. And just everything else just goes around in these lazy circles all around the horizon. It's really easy to do astronomy from the higher end. And then we walk away. We start her up, we walk away. It takes the Anuxa cameras take pictures of the box. We know everything is fine, and then later we'll download the data. One other little interesting trick about this box is that we also tested that in a wind tunnel. The winds are very high. That's partly why the box is there to correct it. And then the front of that box is made with a plastic. It's almost like a Tupperware. And so when UPIC opens up to take pictures, that actually pops. And popping open throws a lot of the frost that's built up on the front of that box off, and also off the cameras. It shakes the box a little bit. Something you can only learn by doing it, putting it in a wind tunnel and actually testing it. But it actually worked. And then later we can download those data. So 2 years later, we flew to the site again and retrieved those data. And this is all sky images in blue-red. I think this is Y. And you can get the colors of the stars. You can also do actual photometry. I don't think these photometry were from that camera, a different camera that was at a different site. But this is actually photometry of Polaris. You can see that it's a pulsator every 4 days, right on schedule. And so you can bin those data together and actually do photometry with that. And that gives you another measurement of the sky quality is by doing actual photometry with it. And these are all the images of Polaris with that camera. And it looks a little messy, and it's partly messy because there was some frost buildup on that lens, and that's why there's so many dots. Each of these dots is every measurement. But you can see they go around in a circle right in the middle of the frame, right where it's supposed to be. So our alignment was good. That's a good thing because we couldn't fix it. So we have measurements of the seeing at each of these locations. We watch Polaris for 2 minutes, each of those, and watch it wiggle. And you can measure from that. The RMS of that wiggle tells you the seeing. But that's just a little robot. And they told us that those mountain locations are very good. The seeing is also good. But you can't do much more from there without building a pretty sophisticated robot. But you can do a lot of astronomy from that red building. So from Eureka, from the mountaintop that's close, the 15-minute or 30-minute drive from Eureka, the Pearl building. And so this is an image from the roof of that building, and all 360 degrees. You can see this box behind the building. This is it here on the ground. And so you can see this is all the way around 360 degrees, and it's unobstructed. So it's a very good location to do astronomy from. In the wintertime, this is seeing it in the summertime. But you can also do astronomy there in the wintertime. And that means, these are actually standard Meade telescopes set up on the roof. There's some very cold astronomer. And our electronics, we've learned from building the robots how to get electronics to operate. So they're in a closed box, an insulated box. You get your computers and storage, data storage is actually in the box right there by the roof. It's taking rapid pictures of Polaris, just like the little monitoring camera, but a bit more sophisticated, is measuring the seeing. And there's 2 of these set up there. And so the learning about building robots makes for pretty good, reliable telescopes. These can actually be left alone for a long time, days at a time. Oops. And so I think at this stage, why don't we go there? Why don't we figure out how we do this? Remember, we can go there in the wintertime now. Let's go on a trip to the top of Pearl in the wintertime. And I think I know how to do that. Thank you. Well, we're going to start from pretty far north, Yellowknife. And that's Mr. Seal and Mr. Polar Bear is going after. So this is the airport in Yellowknife. I think you can watch for them. I think there's going to be several other polar bears in this story. No live ones, only stuffed ones. This isn't our plane, but this is another plane. These are charter aircraft, so we don't have to fly there in a helicopter. We can fly there in a big chartered aircraft. As some of you may know, I mean, aircraft spend more time in the shop than they do in the air, and these are aircraft that are thankfully being well maintained. There's one of our crew checking out a King Air. It's a King Air. Flying up in the north, you learn about all different kinds of aircraft. And we've flown in. What have we flown in so far? The helicopter was a Bell 206. We flew in a Twin Otter. Now we're going to go in that is a Dornier 227, one I'm very familiar with. And yeah, pretty loaded up. We're in the back. People fly in the back 3 rows. The important stuff goes up front. That's all our gear. It's not all the food. Food and fuel go in by ship in the summertime. But our crew and the pilots are up front. Like I say, these are my field notes. So I think I may have only been recording here because we actually had to shut down the first time we went up. One of the engines started making a lot of smoke. I think it's this port side engine. Oh, it looks good now. And so I think we're going to get going now. This is, I think, the second try that day. Middle of the day, I don't know, it's probably, well, could be 6 o'clock in the morning, starting from Yellowknife in February. Maybe it's noon by now with the engine trouble. Broad daylight, as you'll notice. It won't be broad daylight in February by the time we get to Eureka. We're flying out from Yellowknife. There's still trees there. We're going to pass the tree line pretty soon. And getting farther north. Not getting dark yet. Not past the tree line yet. I think what we're going to see, if we don't go over the diamond mine itself, at least we're going to go over the ice road that goes to the diamond mine. There's one of the ice roads. And there's a truck making its way south. I don't know, I've never been on an ice road, but that's scary. It's a long trip. It'll take about 4 or 5 hours to get to, our next stop will be Resolute Bay. These roads wind their way all over the Northwest Territories. We're going to go well past where roads go. When we get to Eureka, it is the longest road in Nunavut. It's 15 kilometers. You don't get anywhere in the far north, the high Arctic, on a road. You get there by plane or ship. I'm not sure what this is. Here we are in lovely Resolute Bay in the wintertime. There's the moon. Even from 76, the moon is at a pretty low elevation and just goes around in a circle. There's our plane being refueled. I think it's probably, I don't know what it was in Yellowknife, maybe it was minus 20 or so. It's going to be minus 40 here. Middle of the day. Moon again. Yeah, the moon is going to figure prominently. Oh, here we are. Now we're in Eureka. This is something called Sublimation Baseball. Oh. That only happens. This isn't even minus 40. This is minus 50. So you put a rubber balloon with some hot water in it, and it is not going to make it to the ground. It's going to all freeze. Oh, straight one. That's better. Yeah, it all freezes as droplets before it gets to the ground. There's another way of testing that too, but I won't get into it. I think this actually is gonna, I thought he threw it on his head. Science is fascinating. Remember, these are all PhDs, or going to be PhDs. We're still all 8-year-olds. I mean, oh, that's Mr. Muskox, maybe Mr. and Mrs. Muskox. This is inside that station at Eureka. It's very comfortable. It's a very modern facility. They've got cable TV and a bar. And lots of polar bear rugs. Is that polar bear number 2, maybe? Pool table. You need to keep people happy. There's a rotating crew, but it's like the Army or the Navy. You've got to feed people well and keep them well. This is a lineup of all the boots. Remember, you're coming in and out from -40, -50 constantly. You've got to have a good mud room. And you sign in to the station, and here are probably all the safety bulletins that you're going to have to read. Safety is paramount at a station. Any kind of accident is already a pretty serious thing. It's going to mean a flight in to get you. And we're going to read. I'm going to make sure I read all these. Notice there's a wolf on there, on that safety briefing. Yes, there are wolves. It's the only resident population of wolves, and here is one of their lunches. Thankfully, this is after lunch. This is the X-Files portion of the show. That's a muskox. That's actually a baby muskox that has been culled from its family by the wolves. They're very efficient. There is nothing left of that kill. And you've taken everything they can, and that's why you're warned. Well, the wolves are not dangerous. They can become habituated to people if you feed them, but we don't do that. Now we're on the road up to the station, up to Pearl from the station, along the 15-kilometer road. Now you're expecting big snow drifts, lots of snow. It's high Arctic. Is there going to be lots of snow? No, it's that much snow. It blows though. It makes drifts, and they're rock hard. It's a very humbling experience. If you get your big 4x4 truck stuck in one of those drifts, it's only about that's yay high, but it's like styrofoam. It's not like fluffy snow. And if you get your big 4x4 truck stuck, it's a front end loader that comes and gets you, pulls you out. Here's the moon. We're now at Pearl. Full moon. Fascinating. Just goes around in a circle. Full moon. Remember, the sun's down. Yep, sun's down, moon's up. Goes around a circle. It's really easy. Actually, I think in this video I'm filming the full moon because there is actually an instrument right at this moment that's watching it. It's called the ATP, the Arctic Turbulence Profiler, and it's a scintillometer. It's measuring the fluctuations of the illumination across the moon's disk, and it's continuously watching it, which is very convenient, right? So you have diodes that are watching the moon all the way around the station. It's on a pole, so it doesn't need a telescope to track it. It's just a pole with diodes along it, and that the moon goes around that. So that's very efficient. Maybe an image of it in a moment. It's quite windy at this site, but still, 8-year-olds. Off for a hike. Hiking around the station. Getting a view of the moon. It sounds windy. It is windy. This is broad daylight. It's February. It's late February. The sun is just starting to come up towards the horizon. It's a convenient time for us to be there because there are the atmospheric science people are starting to show up to do work as the sun comes up. We're not really interested when the sun's up, but before then, it's convenient because there's flights going in and out. So that's a convenient time for us to be there. But we're still going to get some dark skies too. The sun is just starting to get close to the horizon. I think I'm taking an inventory of the equipment we have on site. I can't remember what that is. That's actually part of the station equipment. Thermometers and barometers. This is a view to the southeast. There's actually a higher ridge. It's called Blacktop Ridge. which is a little higher than the ridge that that Pearl is on. Hello, moon. And this is a very, as you can see, this is a very convenient spot to set up telescopes. You'll notice there's railings all along this roof. You are not allowed to go out on the roof above, I think it's 8 meters per second. What's that in 30 kilometers per hour? Because you could be blown off and no one would know. So there's a protocol for when you can go out on the roof. Up to a certain speed, it's okay. Above a certain speed, you can't go out without a pair, and above a speed a little higher, I think it's something like 30 kilometers per hour, you shouldn't be out on the roof at all. Remember, it's pretty close to the research base, but that's still a 15-kilometer road, and the help is a long ways away still. Setting up on the roof, I think we're getting ready to put some telescopes. There's a LiDAR hatch. So this is a big hatch that opens. There's actually large telescopes at this station, the LiDAR receiver telescopes. You shoot a laser up into the sky, you measure the time delay for those photons to come back with a fairly big telescope. One of them is a meter across, but they point straight up, so they aren't particularly useful for doing more astronomy than just watching the laser return. I think these are some cameras that are also doing measurements of sky brightness. It's a very dark site. And there's the ATP. So there's this pole with cameras, diodes, that are just pointed around the horizon at different elevations. You don't need to point at the moon. The moon's going around, and you build extra telescopes to watch it all the way around. Oh, this is inside those LiDAR silos. So the LiDAR telescope points straight. Oh, this is on the roof still. These are standard Meade telescopes, modified only for the cold. You need to change out the bearings. You need special grease for the bearings. Usual grease is okay down to -20, I guess, but not -40. This is a radio telescope on the roof. You can install those sorts of different instruments to test this location. Doesn't look like a radio telescope, but it's a 225 gigahertz receiver, which is monitoring the opacity. This is another standard off-the-shelf. It's not a Meade, but it's a standard off-the-shelf instrument. I think it only costs $200,000. And this is some of the other atmospheric science instruments that are set up. There are solar measurements. So we have other measurements of opacity using those too. And one of those silos. I think we're going to go next. After this, we'll go into one of those silos where those LiDAR telescopes are. Oh, the reason why we're not observing is because, well, the weather's crappy. Sometimes the weather's crappy. There's clouds going overhead. But we have satellite imagery that's telling us when we can go out and observe and when we can't. Remember, we have to be within the restrictions of the wind speeds, too. So we're actually setting up the telescopes by hand. These are in that case, we're actually aligning the telescopes with Polaris in the dark. These are drawings of the building inside. I'm going to show you. We're in one of the laboratories, and we're going to go into one of those silos that has a large telescope in it. These are the as-built drawings for the station. I started my career in architecture. Sorry. I'm just fascinated by drawings. And these are the everything is there. You have a kitchen. The showers. You can. It's an observatory with all the support that you need in order to observe. But it's not for astronomy. It's for doing atmospheric measurements. And these are underneath those tarps are the lasers. I think for my notes, I'm giving myself a picture of where these lasers sit in their labs. And like any observatory, there's a constant compressor going somewhere. you're either pumping something out or you're making liquid nitrogen. In this case, they actually have to make liquid nitrogen on site because it's rather expensive to transport. I think I'm telling the graduate student where to point the flashlight inside this silo. So we're learning also about, because people have been observing at this location, the building was built in 1993. Because people have been operating instruments at this site for so long, there's a lot of tricks that they've learned. How to keep things dry, how to keep, once you've opened the silo, how to cool things down slowly so you don't get frost buildup all over your equipment. So we're learning from them. So that was discussed, also looking at that previous equipment to learn from that. And now we're coming down from the station. After a long night of observing is, well, the sun isn't going to be up, but it's going to be daylight essentially, like this, for 2 or 3 hours. So that's a pretty long night. Yeah, the required photograph with the 80 degrees north sign. No one is allowed to leave without having their picture taken by it. This must be a newbie. So many graduate students go to work at this site. This is a great place to learn how to do very difficult work under demanding circumstances and keep your priorities straight, get your work done. It's a great learning experience. The next step is going to space. We're going to launch a weather balloon. This is why the station's there. Apart from radio communications, it is a site that 2 stratospheric measurement balloons are launched each day. They're preparing them. This is actually a helium balloon. A hydrogen balloon, sorry. Usually helium is used, but this is actually a hydrogen balloon. They make hydrogen on site. Well, I think we're actually going to see the equipment that makes it. And this is what a launch looks like. He goes out. He's got underneath is the sensor. We're not going to get this back, or the Environment Canada is not going to get this back. Not moving much, is it? It's dead calm. Typical conditions here, wind speeds are below 2 meters per second. It's very calm, and it goes straight up. They do that every day. I've been doing so for 50 years. We have a very good picture of what the atmosphere is like above Eureka. Making hydrogen. Really? Don't you have any experience with what happens with hydrogen? Yes, they have lots of experience with what happens with hydrogen. They're very safe. I think we have to, before we go in this room, we have to go through a procedure of making sure there's no static electricity on us, because a spark in this room is a bad thing. But it also gives you a picture of how difficult it is to transport things. Transportation is it's all about transportation of people and things to such a location. So it's very expensive to transport in the helium, so they have to make hydrogen on site. And this is us going home. Almost broad daylight. This is actually sunrise. This is the day of sunrise, February 23rd, I would guess. I'm pretty excited. We're actually going out on that day. We're going to, so the sun has not risen yet, but as we climb, we'll get to see it. Waiting for the plane to come. So remember, we've been there for a month. This is, we flew in the dark, as you saw, and we're flying out in daylight, but we're actually flying in and out. But in between, there was no flights in and out. And a flight in to get somebody would have meant there was something bad had happened. So it's pretty exciting after a month there. Don't worry, we've had showers and everything, so it's all very comfortable. But now we're flying out. It's quite an exciting day when the plane does arrive. It's a similar aircraft that came and dropped us off, maybe the same. And we're back on our way to Resolute Bay from exciting Eureka International. It's part of the infrastructure that is from the Cold War, where you needed landing sites that are along the northern routes. It is an international airport. Flights will come in from elsewhere, Greenland. It's not part of Canada. But this highlights the difference between Antarctica and Canada's high Arctic. We are flying in and out like a regular trip to an observatory. In Antarctica, not February, of course, because the seasons are reversed, but in midwinter, effectively, you cannot fly in and out. You're stuck. Once you go there in the fall to South Pole, for example, you are going to stay there. There's going to be no flight in or out until the spring. Under very special circumstances, it has only happened, I think, maybe twice in history has there been a flight to the South Pole in midwinter. And who do you send there? Yeah, you guys know, it's Ken Boric Air. This isn't Ken Boric Air, but these guys are the same kind of we can do it pilots. I love talking to pilots. Is that number 3, 4? I met the fellow that shot this guy. That is a very large male. This bear was taken down with a bow. Amazing. That's some real hunting skill. Here's our lunch. I'm not sure why it's Canadian Forces. Maybe that was just cheap. Noting my location. Todd Inlet is very close to my house. That's in British Columbia, on Vancouver Island. Going home. Oh boy, that's a nice lunch. Sandwich and cookies and... Yep. Yeah, the Forces eat pretty well. And here we are in Yellowknife again. I think these are just some snaps of the inside of the museum, which is fascinating if you get a chance to go there. I think there was a model of a twin otter, which is required, I think, as well. The workhorse of the north. Here's Mr. Arctic Fox. Here's Mr. Polar Bear. That's number 4. And there's some Inuit pants made from polar bear. Sure, they're very warm. And Mr. Musk Ox again. And some tools of the trade. Fishing implements. I think we've learned from looking at all these instruments, you make the right tools, you catch the fish. This is a great display. This is one of the best museum displays I think I've ever seen. You actually go up to the screen and you make a solar flare. Awesome. That is the kind of inspiration you give to a kid and they go, wow, I just made a solar flare destroy the Earth. Well, at least I shut down every radio and the International Space Station as well. And I think the end of this clip is actually shows a diamond that was taken aboard a space shuttle to the space station from the diamond mine that we flew over in the beginning of the film. It flew and returned, and I think it is also mounted. There it is, a high Arctic diamond in this beautiful sculpture. And just like pearl, it's a diamond in the rough. Beautiful. It's big too, got a large rock. So that's our trip to Eureka. And then this is just a few more things about using the right tools on that roof, and learning from past experiences in observing from this location. So that's a lot of frost on those telescopes. But that's typical after these high wind periods. And from that we've learned. So it's also, you see the tops of those telescopes. This is on a different mount that's called called ukalik. Ukalik is the snow hare in Inuktitut. And like it stands up on its hind legs when it wants to look up. But otherwise, it huddles, and that's what this telescope is going to do. It's going to point down when it's not observing, because that's what you want in order to reach the thing, in order to clear the glass off. If you want to stare straight up and want to maintain your good seeing, all the heat is from the electronics that are in the only heat is from the electronics in that telescope underneath. That's rising straight up, and that's going to spoil your good seeing. So you don't want that. So you don't want to heat the top of the telescope, which is what you normally do, right? If you have a dew shield or you have some way of keeping that Schmidt plate, these are all Schmidt-Cassegrain telescopes. If you want to keep that Schmidt plate clean, you want to heat it, but you can't do that here because you're going to spoil the seeing, and the seeing will bubble up above the telescope and spoil it. So you want to point the telescope down and blow on it with a fan. That can be automated very easily. Or wipe it off with alcohol. Just go up on the roof. You can in the wintertime, go up on the roof and fix it. The other telescopes, so if you don't need the good seeing, then you can just heat that window. So these are those two smaller telescopes which are on the roof. These are called the Ockhams, the Arctic Wide Field cameras, and they've done some very interesting astronomy. The top one is an algol, and the bottom is the plots are of a binary, and this one is actually of a planet transit, a known planet transit, just as a demonstration. These are published in refereed journals. So you can do real astronomy. That's if you don't need the good seeing. You just heat the window and take photometry. Photometry may not matter if the seeing is good, but if you want to take sharp images, you'll need good seeing. But ukalik, like it's the little picture to the side, it needs to point straight up at Polaris, for example, to take seeing measurements. And so there you don't want to heat that window, and that's what I was talking about when I meant. You have to learn from the locals how to keep things working. And these are more pictures of that. And so that's quite a capable instrument. And so from this, we actually know the seeing is very good from Pearl. The seeing is about 0.76 arc seconds on median from the roof. So it's better than Dome C from 8 meters. And these are all the tricks of the trade, learned by being there. Other tricks of the trade. Last trick of the trade. For not getting stuck in the snowdrifts. Thank you. Entertain questions?
Jeff, are you able to take questions?
I would love to.
Anybody have any questions? Chris has the microphones there. Go ahead.
Eric, is that now continuing to function, the telescope, is a more or less permanent observatory?
No, not the seeing measurements are essentially completed. So my job as the site tester is to show what the quality of the location. The quality of the location is fairly well understood and shown. There aren't continuing astronomical observations from the location right now, although there are plans to do more, to have larger telescopes, and those things are being considered at this point.
How long are the nights truly dark in the north? There's a long time when the sun is way below the horizon, but my understanding, if it's correct, is that there's also a tremendous amount of twilight.
Exactly. Yeah. So it's the sun is getting lower and lower in the fall, so you have a long twilight. Yeah, the twilight starts in September, and it hangs around until October. The sun doesn't actually really stay below the horizon until into October, from 80 degrees north or south. And then you have the problem is also the moon will come up, right? So the moon will also illuminate at some of those nights. So it's actually the windowing isn't perfect darkness for that 4.5, 5 month chunk that you're kind of expecting. The sun is actually below the horizon. It doesn't get very low below the horizon, but it does get astronomically dark. So the sun gets low enough, the moon is down enough that above air masses of 45 degrees, it is dark. And for a long period, for at least that full 5 month period, there'll be periods of astronomical darkness. Thankfully, also those dark periods are not windowed by cloud, right? So we also measure the cloud period. So it's not just that you get that darkness, it's also that you get dark clear skies, and those last a long time. You can't get 100-hour periods of darkness like you can there at mid-latitudes. Right? It doesn't happen. It only happens for 11 and a half or 12 at most. So, so you have very long periods of dark, clear skies.
Question here?
Hi,
I'm sorry,
the wind turbines that you use for your Polaris experiments, you had enough energy for your experimentation and for the webcams. How much energy can you get from those wind turbines?
Well, I don't know what it would be in, you mean like in watt hours, or I don't know that number off the top of my head. But we can, everything is built to operate at very low energy consumption, right? So you're talking just total like a watt. The station is taking a watt. And during the periods of high winds, which can last for a day or two, you can generate enough power to operate that 1 watt, 2 watt system for a week or so at a time. So I think you could probably calculate from that. But it's a pretty significant chunk. The problem is that you have to store that. And that's a complication of battery chemistry. And also keeping the batteries warm. Batteries don't like being frozen. They can't be frozen to -40 for very long and still work. So that would have been the calculation that goes in is how many batteries can I take on the helicopter and afford to carry it in the helicopter, and it lasts that 2 weeks. So that's the calculation that you do, and I'm sure we've thought very carefully about how many batteries to take and what particular chemistry to use that would survive its lowest temperature that it's going to get and still have some energy left to warm itself, right? So you run a coil to keep the batteries warm, to keep them destroying themselves, but also keeping enough energy to run the station as well. So I don't know what the actual energy content is, but no more than 100 pounds of batteries, I think, is something like that.
Question here, go ahead.
Yes, to what extent do the northern lights impact the work that they're doing?
You mean Aurora?
Yeah.
No Aurora. Aurora to the south. No. I'm sorry, that sounded just facetious. So, so the magnetic North Pole is very close to Eureka. You're actually in the middle of the auroral hole. So the aurora are around you. You do see them. They're on the horizon usually, when you see them. But the aurora are to the south.
And, do you have Gary next, or is it?
Okay, Ron McNaughton. Ron? Thanks.
What is the chance in 20, 30 years that there'll actually be a professional-sized 10-meter type telescope on top of one of those mountains?
Oh.
Well, that's a tough question. We're having trouble building a 20, 30 meter class telescope on a mountain that we have access to. Astronomy is a careful, well thought out, long game. And I've been in astronomy for 20 years. And I've seen observatories develop, and it's a very long process. And so I don't think that the logistics of it for the high mountains is very difficult to imagine. A larger telescope and something that can operate as a robot. So that's a pretty small telescope. But from Eureka, you can imagine something that's quite more, or from Blacktop Ridge, for example, a higher site, something that is a more sophisticated, larger observatory that we're not getting there yet. But many other observatories have developed over a longer time as well, before they had anything that's like that too. So that's not out of the question.
Question over here.
How do you cover all those daily instrument flights, balloon flights? How do you cover the instruments themselves?
Well, recover. You don't. No, those are throwaway measurements. Those the stratospheric balloon that I showed in the video. Those aren't mine. Those are part of Environment Canada's daily, where they're taking instrument program. But you don't recover those. They're I think it's not my field, but I think they're very light. They wouldn't hurt anybody when they come down. They're in a styrofoam box. They're quite small. I think they also have a card in them that says where to mail it if you get one. and boy, would that be fun to find one.
The card says don't touch it, says the battery's probably broke.
Yeah.
The card says don't touch it.
Oh, don't touch it.
Okay, John?
In civilized areas, it's a parachute. There wouldn't be a parachute on the instrument there.
Okay, John, go ahead.
Yes, the photometer you had made your showing the variation in Polaris. Would that be sensitive enough to do transiting exoplanet searches?
Not the one that I showed the light curve for Polaris. That's not quite good enough, but it's just enough to show it. But those Ockhams, the ones that were more the boxes on the roof of Eureka for Pearl, those they can do millimag photometry. If you don't need good seeing, and if it's a bright star, right, like Polaris, you don't need great seeing to do an excellent measurement. You have lots of photons, and they're not spread all over the place. So you can do millimag photometry with that, and it did. That's demonstrated. So world-class photometry from that.
Charles in the back?
Yeah, like you, I was up there a long time ago, a little bit further north actually, and I did not see any aurora, and I was wondering why. And of course, it circles the whole northern pole. My question is, why?
Oh, thanks. Also not my field. So, sorry, I don't know the answer to that. It's certainly a geomagnetic issue. I'm actually a galaxy guy. So my expertise is quasars. So if you have a question about quasars, then I'm happy to answer it. Sorry, I don't know.
Are there any more questions from anybody? Okay, I think what we'll do is we'll pause here. Eric, I want to say thank you very much for a very interesting travel log, an astronomical travel log. Just saying who's away. Anyway, that was great, and it was very nice for Bridget and me to watch this because our daughter, of course, works in the Arctic. This is where she met Eric. These guys flopping around in minus 50, batting. Boiling balloons out of the air and everything like that. But the work they do, it's incredible what you have to do. And you mentioned yourself the conditions that people are having to work under. And who mentioned to me about in the outreach doing a scientist or an astronaut simulation where you get the kids wearing big gloves and then try to put puzzles together? There we go. I mean, it's the same type of thing. So I was just thinking about you because of the comment you made. And it's the same type of thing you're having to work with. You can't go out and just take a glove off and just...
Nope. No, you never put a bolt in your mouth.
So anyway, Erica, we have a little thank you gift from us. Here's some Canadian maple inside here that we've had manufactured in Ottawa because it's our maple GA. But anyway, thank you very much.
Thank you,
that
sir.
was just wonderful. Thank you. Thank you. Very exciting.